Hello everyone, welcome to our final video for Unit 4-5. In this video we're going to talk about properties of the Laplace transform beyond just like linearity and stuff like that. I think these properties are really neat and this is one of my favorite things to teach. Let's do this one first, the one with the sign. Okay, so we're going to learn about something called translation in S. So let's recall something. In the previous unit, 4-4, I gave you this Laplace inverse identity. Now I gave you technically c times beta in the numerator, and then the c showed up here, so pretend c is 1, right? So what this says is that the Laplace inverse of beta over s minus alpha quantity squared plus beta squared must be e to the alpha t sine beta t. But I didn't actually tell you how we got that. And furthermore, you'll notice that because the Laplace inverse of this expression equals e to the alpha t sine beta t, the Laplace transform of e to the alpha t sine beta t must be beta s minus alpha squared plus beta squared. I never actually showed you how to get that, so now we're actually going to discuss that right now. So every time you do the Laplace transform, you get a function of s. And I want to make that very clear here. All right, well, let's just work from the definition. So the Laplace transform of e to the alpha t sine beta t, by definition, is the integral from 0 to infinity of e to the minus st e to the alpha t sine beta t dt, right? Now I can clean this up a little bit. You notice this is the integral from 0 to infinity e to the minus, and now you'll notice that these two powers of e can combine. I can add them together. So I get minus st plus alpha t. So I'm going to factor out a t on the right, and now I'm going to factor out a minus. So the s, it should look like minus quantity s minus alpha t, right? If you need, like, just expand it back out and make sure I'm correct, but I think I am. So you'll notice that this looks an awful lot like the Laplace transform of just sine of beta t. Because think about it. Now, I'm not putting any equal signs or anything like that, but what is the Laplace transform of sine beta t? By definition, that's the integral 0 to infinity e to the minus st sine beta t dt. So notice these two things look somewhat similar. They're not exactly the same, but they look somewhat similar. In fact, what you notice is that instead of plugging in s, I'm really plugging in s minus alpha. So this expression here is actually the Laplace transform of sine beta t, but it's no longer evaluated at s, it's evaluated at s minus alpha. Okay, well, what is the Laplace transform of sine beta t? The Laplace transform of sine beta t is beta over s squared plus beta squared. Well, now if you plug in s minus alpha for s, what do you get? Ta-da, right? You get exactly what I said you should get, right? So this is beta over s minus alpha squared plus beta squared. Okay? Let's see this with another example. So you'll notice I also gave you this identity here, that the Laplace inverse of 1 over s minus alpha squared is t e to the alpha t. And so therefore the Laplace transform of t e to the alpha t must be 1 over s minus alpha quantity squared. Okay? That's what I'm saying here. Let's see what we get. So the Laplace transform of t e to the alpha t, by definition, is integral 0 to infinity e to the minus st times t e to the alpha t dt. Well, I think you can see I'm going to do the same thing, right? This is the integral 0 to infinity e to the minus s minus alpha in parentheses times t dt. Well, this looks like the Laplace transform of just t, right? but no longer evaluated at s, except instead it's evaluated at s minus alpha. So this looks like the Laplace transform of t evaluated at s minus alpha. So this is not multiplication here. This is what's known as function notation. We're saying it's whatever the Laplace transform of t is, and then we replace s by s minus alpha, right? Well, what is the Laplace transform of t? Look on your chart. The Laplace transform of t is 1 over s squared, but now replace s by s minus alpha. Ta-da, right? It works. Okay, so let's try to generalize this rule now. Let's come down here. Let's suppose that I call the Laplace transform of my function little f, I call it capital F of s. We've seen that before. When you do the Laplace transform of little y, you get capital Y of s, right? Okay, so that's nothing surprising there. Then if you multiply that function by e to the, and that should be alpha t, my bad. If you multiply that function by e to the alpha t and then do the Laplace transform of that, what you get is the same Laplace transform, only you shift it by alpha, right? Okay, so this is what's known as the translation property. So that's the translation property of the Laplace transform. Okay, so now let's come to the derivative property. So here, this one's a little bit harder to see, but what we're going to see is that multiplying a function by t and then finding its Laplace transform is somehow going to correspond to a derivative. Okay, this is a property called intertwining, which I'm not really going to get into, but let's see how it affects our problems here. So let's look over here where I have we know. We know that the Laplace transform of sine beta t is given by this definition here. And by definition, the Laplace transform of t times sine beta t is given by this definition right here, right? I'm just using the definition of the Laplace transform, nothing crazy happening. So here's what I want to do. I actually am going to find the derivative of the Laplace transform of sine beta t, bt, I guess. Okay, so I'm going to compute the derivative. Well, this is the derivative of, by definition, this integral. And you might be a bit suspicious as to why I can do this, but note that this is actually a function of s, right? And so I'm taking the s derivative of a function of s. So these integrals don't cancel because this is an s derivative, whereas this is a t integral. So what I'm going to do, and if you want to learn more about why this is valid, come see me in virtual office hours. But I can actually pull the derivative inside this integral here. And you guys are familiar with derivatives where you have multiple variables. But notice every variable except for s is going to be treated like a constant. And so this is the integral 0 to infinity. Now the derivative of this expression is minus t e to the minus st times sine bt dt, right? Sine bt gets treated like a constant, it has no s's. And so it just stays put when you multiply it by this function of s here. Ah, well look. This is minus integral 0 to infinity, I'm pulling the negative out, e to the minus st times t sine bt. Does this look familiar? Well, yes, this is the negative of this Laplace transform here. So this is the negative of the Laplace transform of t sine bt. Okay. And so what do we see? Well, if I just multiply both sides by -1, I see that the Laplace transform of t sine bt is the negative derivative of the Laplace transform of just sine bt. So here's the punchline. I can exchange a variable multiplying a well-known Laplace transform, but I have to pay the penalty of taking a derivative of the known Laplace transform. We'll summarize this a little bit more later, but let's look at the next example. All right. Well, now let's compare these two in the next example here. The Laplace transform of t squared e to the at. Actually, I can use my translation property, right? Notice f of t is just t squared. Here's my e to the at instead of alpha t. So as long as I know the Laplace transform of t squared, which I do, look on your chart, it's 2 over s cubed. I just replace s by s minus a in this case, right? So by the translation property. This is the Laplace transform of t squared evaluated at s minus a, right? The Laplace transform of t squared is 2 over s cubed, so I replace s by s minus a. And there we go, right? But now let's look at the second derivative of the Laplace transform of e to the at. So Laplace transform e to the at. I want the second derivative of that. So Laplace transform of e to the at is this is one of our fundamental Laplace transform here. This is 1 over s minus a. So I want the second derivative of that. So the second derivative of 1 over s minus a is the do one derivative. You get negative 1 over s minus a squared. And now you still need to do one more derivative, right? And you get 2 over s minus a cubed. Okay. Do these two things look familiar? Yes, I think so, right? They're dead on equal. So what we found is that the Laplace transform of t squared e to the at equals the second derivative of the Laplace transform of e to the at. Right? And now let's compare above. What did we find here? We found that the Laplace transform of t sine bt equals negative derivative of Laplace of sine bt. So it looks like every time I do two derivatives, that negative sign goes away. So can we capture what's happening here? If I call the Laplace transform of a well-known function capital F, then when I multiply by a power of t, let's see what happens. Well, when I multiplied by t to the first, I got a minus sign, you see up here. And when I multiplied by t squared, I did not get a minus sign. I got essentially a positive, right? So I think what's happening is that you get a minus 1 to the n, and then multiply by the nth derivative of that well-known Laplace transform. So all of this is very abstract, but I want you to remember these two properties. This is called the derivative property. And so let's talk a little bit about the homework here. So for numbers 1 and 2, I want you to use the translation property to find these Laplace transforms. So you'll notice here I'm multiplying by e to the minus 6t. So this is the same as the Laplace transform of just t, but you evaluate at s minus negative 6, so s plus 6, right? So I think you know what the Laplace transform of t is. It's on your chart. So instead of s, you just plug in s plus 6. You see how that works? Here, we have the Laplace transform of t to the 9. Use n equals 9 on the chart. And instead of plugging in s, what do you think you plug in? S minus 7, right? Okay. Here I'll say for these two, expand out first, and then you'll have a few Laplace transforms, each of which you can kind of use this rule for. And now here we're just working backwards. Some of these should kind of feel familiar. And now here we're going to use the derivative property. So this one, let's just talk about, like, let's say the first one, for example. Now, every time you see an extra factor of t, this is minus 1 to the first times the derivative of the Laplace transform of e to the minus 10t. And now look on your chart. You know what the Laplace transform of e to the minus 10t is. So take the derivative of that and multiply by negative 1 to the first, right? This one here, you'd multiply, you'd have a minus 1 cubed times the third derivative, right? Because you have a 3 here. This one you'll be doing a second derivative of whatever the Laplace transform of that is, and so on and so forth. So you're not supposed to like recreate all of this work that I did here to kind of convince you, I hope. Instead, you're just supposed to use the properties, right? So use the derivative property of the Laplace transform and use the translation property. Okay, so that's it for Unit 4-5. Please see me in virtual office hours if you have questions about these examples, but I think they're kind of neat.